do have a question, Dr. Susan.
Question?
Yes, never mind, you have it there. I was gonna say, can we review again what an organocuprate is, but.
Well, we're doing that now. I think that's where we left off then.
Okay.
That's what we need to look at, right? Number 7, yes. By the way, the above reactions, okay, I said work with an ester, okay? These three esters up here, LAH or diol ester, you can displace the OR group just like the chlorine. With these reagents, you can, okay? Make that note. Cuprate, 7, this is where we left off at? Okay, up here with this Grignard, we had sort of a double addition. Addition, up, down, kick off the chlorine, that gave us something, we had brackets around it, that was a ketone, right?
Yes.
But then we came in with another equivalent of the Grignard, and so ultimately we used 2 equivalents here. A lot of times this may be just written as like excess for these reagents. But we used 2, we had a ketone, and then it reacted again to get what was the final product? Not a ketone, but a
Tertiary alcohol.
tertiary alcohol in this case. Can you stop the ketone? Yes. Number 7. If you use an organocuprate, you can stop at the ketone. It's a great way to make ketones. What is the structure of this here? Copper lithium. Well, lithium is always plus, so what's the charge of the 2-ethyl copper?
Minus.
Must be minus. Well, what is it? This is actually a copper with 2 ethyls. Okay? Now, transition metals can make covalent bonds to carbon, and sometimes. Now, we can consider it fully ionic. Just like Grignard, we can show Grignard as sort of covalent. We can consider it fully ionic. But this is a little bit complex. But this is actually a minus copper. Can copper be minus? It's actually a little bit unusual. Usually transition metals are positive. Okay? But it can be negative. And that's what you have here. And then there's a lithium positive sitting with this. But think about it. We've actually seen boron and aluminum minus, right? Sodium borohydride, the boron is minus. What does the boron do? It has these H's on it, but it's mad. So what does it effectively do? What does this act as?
The source of hydride?
Hydride source. It says H, okay, you and your electrons go. Same thing here, the copper is not happy. Hey carbon, you and your electrons go. So what is this really? I could consider this R groups, but this is going to be,
Negative ethyl group.
when this goes, it's the R minus. It happens to be, in this case, ethyl. It's very analogous to that. Hey, get away, take your electrons and go. So it acts like this, but this is just like what this was, right? Isn't this also the ethyl anion? So it's another source of ethyl anion, but it tends to be less reactive. And it's also got the magic of copper, which we don't have time to kind of go into, and never could fully go into it. And it's called an organocuprate, because it's a copper ion attached to an organic here. Organocuprates tend to be less reactive than Grignards. Organocuprates will react with acid chlorides only once. And you can consider it like this, okay? And these electrons end up, okay, down. You cannot do this on Quizzer mechanism. This is me saving ink. You know what we're doing here? When it goes up, that's an O minus. Show that. Then back down, okay? And what do we get? We just do our acyl substitution. There's no proton here to worry about. And now what's on the carbonyl?
Ethyl.
An ethyl. And that's it. You get a good yield of that. So half of this is understanding the reagent stuff. Very reasonable to try to understand that. The other half is just memorizing that it just stops at half. At one addition, you get a ketone. That's just, you gotta just memorize that, right? All right, great way to make a ketone. Question?
Will an organocuprate ever react to give a primary alcohol? Will we ever get an alcohol with an organic?
Will it add again?
Yeah, I'm asking because there's a question in the book that says organocuprates react with acid chlorides to yield primary alcohols after hydrolysis.
No.
False.
These react with acid chlorides to give
Okay, so this is the only product we'll
ketone.
get.
That's it. If it added again, like up here, see Grignard's added twice, and this kept going, what did we get up here?
Tertiary alcohol.
We got an alcohol. Was it added twice? Cuprates only add once. And cuprates only add to acid chlorides. They don't react with esters, which again implies that cuprates are less reactive. Question?
So as for like Dibol, is that like, it doesn't react with amides. Is that because like amides are like not as reactive as say like acid chlorides, for example? Like it won't like yield the aldehyde intermediate with an amide.
From an amide?
Yes.
Well, I'm not going to say that.
Oh, okay.
Sometimes they can't. Why do you ask about amides?
Oh no, I mean I was just like reviewing a little bit, and the book mentioned like that amides just like just an extraordinary case in that they remove the carbonyl when you react with lithium.
We haven't done that reaction yet, and you're talking about LEH, not Dibol. Sometimes other things can react because aluminum can be Lewis acidic. And there's some reactions that can actually happen, but I'm not going to tell you they can happen because I don't want you to get in trouble. So I don't know where you're coming at with this. The reduction of the amide we're going to see on the next page. Okay, we made a ketone here, cuprate. How do you make cuprates? There's a note down here at the bottom. You can make these from copper iodide, alkyl lithiums, you actually. So you take copper iodide, which is copper plus. And you can actually add R groups to the copper plus, for example, in the like R lithium, which is going to be R minus essentially, which is what we used up there, like ethyl lithium. You actually make the cuprate from ethyl lithium. And these will just add to the copper, but you add twice. Each time you add, you're taking the copper down. But you can find this in the book. Because if you then come up here with R, whatever the copper was there now has an extra electron because it has the bond and you count one there. Well, if copper plus has an extra electron, then it's copper 0. If you do it again, then it has 2 extra electrons. And from there, 2 extra electrons takes you to -1. But you can find that in the textbook about how organocuprates are made. Okay, over here, amide LAH. Someone predict a product here? First product, it may continue on. What's going to happen here?
First part being aldehyde and the second would be a primary alcohol.
Okay. H minus. Now these strong nucleophiles can react with amides. Okay. Product here is not a primary alcohol. It's actually a primary amine.
Yeah.
Product here is this here.
What's the name of that product? What would you name that?
That's a primary amine.
Right. What's the like I?
Heck,
Well, it's called benzylamine. I don't know if that's IUPAC. You call it phenylmethylamine. Because if the benzene ring wasn't there, it'd be methylamine. You just have a phenyl. It's called benzylamine. We've seen the benzyl group before, benzyl chloride, benzyl alcohol. That's benzylamine. H minus here. H minus, this will add here electrons up. Get to this point here. Nucleophilic addition of the hydride. What's next? Eric, what do you suggest is next? Electrons back down, kick off.
It attacks the aluminum,
What's the next?
the oxygen.
Okay, I would propose maybe bringing this down, kicking off the nitrogen.
Would that be
That would give what?
an aldehyde?
Aldehyde?
It's not.
Okay, but that's not it though. The product still has the nitrogen bonded to that carbon. Instead, okay, no, this doesn't happen. One reason it doesn't happen is because that's not a great leaving group. It could. We can hydrolyze this amide, hydroxide adds, then you come back down and kick that off. But instead what happens here is, what's the remainder of the aluminum here? We can't just ignore it.
LiH3.
ALH3. With aromatics, we use aluminum trichloride as a Lewis acid. Okay? These electrons then coordinate with the aluminum. And I'll show this out. The aluminum becomes minus. And by the way, at this point, the aluminum, this becomes another hydride source. Because now the aluminum is minus again. See, this can actually serve as, I think, 4 equivalents of hydride because it serves as one. Then something complexes with it again. Now it can shoot out another because aluminum is no longer happy. But let's go back down here. By the way, this one can be shooting out hydrides. And let's get it to neutral. Because that may look better. What's that, ALH2? At this point, see back over here, instead of the oxygen coming down and kicking off the nitrogen, instead at this point, the nitrogen comes in here and kicks off the oxygen. And that gives, I'm going to draw this H up now. We now have what, double bond to nitrogen? H positive plus what? Plus maybe something like this. What do we need to do to get our product, which I erased?
Have hydrogen.
Another hydride come in?
Uh-huh. We need another hydride here. The product was the primary amine, yeah?
Yeah.
This is where we got to take care of the proton, and I don't think most books do. I'll go ahead and do it. Now if we come in here with another hydride, so this can sort of give another hydride. If these electrons move in here, then it can shoot out another hydride. I'll do it this way, shoot it out, and if it comes in here, and these electrons move here, what does this give?
Couldn't you already use the
You
hydride
already
that
shot
it
one out though.
that it lost when it went from AL3 to ALH3 to ALH2?
Yeah, but what I said is all four of these H's can eventually become hydrides.
Well, I guess what I'm saying is that like when it loses that hydride in that step, is it just kind of like floating around and already available to do that without the ALH2 having to lose another one? You see what I'm saying?
No, I don't see what you're saying.
So when you go not
This came when this is shot out of hydride, we get this.
Yeah,
This
but-
kind-
yeah, and then from the ALH3, when you said to make the aluminum neutral, it lost a hydride. So now is that hydride just available in the mechanism to come back in later?
the one that we lost here?
Yes.
Yeah, because maybe it went reacted with another molecule of the amide.
Okay.
It started another, I'm just doing one conversion. You got to do 100 bazillion in your class.
Mhm.
Ultimately, all the hydrides become, all the H's become hydrides at some point.
Okay.
That's why it gets a little convoluted.
Could it also be concerted when it shoots that second hydride, it attacks the carbon, kicks off the oxygen without forming the resonance structure there? Or without forming the positively charged nitrogen?
This here?
Back farther to where you kicked off the hydride for the first time there. The second structure you drew. Yes, it's a concerted attack from the hydride to the carbon, kicking off the oxygen.
You mean here?
Yes, sir. Because wouldn't there be a slight pull because of the negatively charged aluminum?
You mean push? Pull by what? A negative aluminum is not going to be
my
electron
bad.
withdrawing. A negative aluminum is an electron donating.
Yes, sir.
Okay, I don't know if this mechanism is how known, proven it is. Here we go. Hydride add here. What does this look like? If that was an oxygen, this almost looks like a what? Protonated carbonyl. Okay? It's almost like a nucleophile coming in and adding to a protonated carbonyl. Okay? But that's an imine though. And that would give you the product. Basically, instead of the nitrogen getting kicked off, it's actually the oxygen that gets kicked off. Sort of turns the tables. And how does the oxygen get kicked off? It coordinates with the aluminum. Aluminum is a Lewis acid. So I'm showing coordination there. I'm sort of taking care of proton here. Because when I kick this off, I really didn't want to have two minuses here. So I sort of relieve the minus charge of the aluminum. It's going to act as a hydride source again. We come in here, and this is indeed final product. The only thing I don't like about this here, and I'm not going to go into it much more, is this looks acidic. Well, hydrides are basic. I think the H is first going to take one of these. And then it comes in subsequent to that. But I've seen books just do it like this. I just have a problem with this because hydrides are basic. That looks like an acidic proton sitting here. Okay? Otherwise, this is a common reaction. It's got some sort of generic things to consider here. And instead of additional elimination, you get an aldehyde, which is what you suggested originally, Nick, yeah? And then maybe the aldehyde gets further reduced to the alcohol. You actually don't go that way. You actually ultimately get the amine. Ultimately, what does it do? If you think about it, it's a deoxygenation. Look at the amide and remove the oxygen. And that's what you get here. Now, of course, the carbon, the two H's are put here instead of the oxygen. All right? Same number of carbons, benzene, carbon. There's a reaction we'll see a little bit later where you actually lose a carbon. Not here, though. You essentially just lose the oxygen, replacing it with two H's, right? Deoxygenation of the amide to the amine. Does it have to be a primary amine? No, because you can have R groups on the nitrogen. If there were R groups on the nitrogen, they'd still be there. So you can make primary, secondary, tertiary amine. Tertiary amide is going to give tertiary amine. So it's a little bit of a twist there where the oxygen got kicked off instead. Is that basically what you saw in the textbook?
Yes.
Because you were trying to refer to that.
Yeah.
Okay, nitriles. What can nitriles give? With LAH, which is a reducing agent, it may actually be easier to start with hydrogen, because hydrogen with a precious metal catalyst gives the same product as LAH. Now hydrogen here gives the same product as like if it was an alkyne. If we had an alkyne, like this, I'll do a internal alkyne, and we treated this with hydrogen, and like palladium on carbon, what would we get? This gets fully reduced down to the alkane, right? Could we stop this at the alkene?
Only if you have a poison catalyst.
Poison catalyst, okay? Now the cyano group is a, okay? So we'll draw those as carbons there. Instead of carbon triple bond C, it's carbon triple bond N. It's the same exact type of reaction. This is going to give with this R, that becomes CH2, and the nitrogen becomes what?
NH2?
NH2. Basically, your 2 pi bonds get reduced, just like the 2 pi bonds here get reduced. And so this will be a primary amine. It has to be, because you're never going to have R groups on the nitrogen of your nitrile. And so this is the easier, it's analogous to the alkyne reduction. Triple bond reduction all the way down, triple bond reduction all the way down. Okay? So that's actually more analogous. Well, guess what? LAH gives the same exact outcome. And so the product here will be carbon, right? Same number of carbons, just this becomes CH2, that becomes NH2. CH2, NH2. In the end, the cyano group can be reduced down to the primary amine. It's actually a reasonable, useful synthesis of primary amines. Right here. Question?
So in the workbook, there was a similar problem where it would be an N2 with the same principle apply, where the first nitrogen would have NH2 and then NH3 at the end of the reaction.
What do you mean N2?
It would be an R group and then N2 nitrogen with a triple bond. So would it still result?
I don't know what you're talking about.
So
Can you show it to me?
Yeah.
What do you mean N2?
So instead
R N2?
Yeah,
Like that?
yeah. So instead of the
In my
C-
workbook, where'd you see this?
it was in the first couple of pages.
R N2?
Oh, the R.
Is it mechanism?
Yeah.
Written like that?
Oh, no, it wasn't. I didn't know what the R, I couldn't remember what the R was, but it was this.
It wasn't N3, was it? N3 is azide.
It was a diazonium reaction. I don't recall exactly.
Okay, I mean, okay, diazonium then.
It was this one.
She
This
found
is
it.
how.
But N2 is,
Because we're taking the N2
I know too.
and yeah.
Yeah.
okay, diazonium?
Does that just replace it?
It started off with
She's
the
talking about.
benzene, and then there was a Honer reaction, and then the second step after that would be the H2 and hat.
I think because you put a nitro group on the benzene, and then the second step is the reduction. Right here, number 1.
That's hydrogenation of a nitro group to give an amine,
Okay.
which was test 2 chemistry, which is benzene chemistry. Nitro group, right? I mean, nitro groups, that's not N2, it's NO2.
Okay.
I mean, nitro groups can be hydrogenated to the NH2. That's reduction. You did a reduction in lab, but you did it with a metal.
Okay, yeah.
You can also do that with hydrogen.
If it was NaNO3, then that would be.
Well, the NO3 was used to make the nitro.
Okay. Okay.
The reduction was the second step of that. Very important chemistry. I mean, because the HNO3 is used to nitrate, which you also did. Are you taking the lab? But LAH gives the same thing, but it's not a hydrogenation. And I'm not going to go through this, but with LAH, you actually, the hydride comes in here, and it's a mechanism you can do with arrow pushing, ionic mechanism. The electrons move here. Maybe we can go through this some. So that would be N. Now an H here, yeah, and the nitrogen is now minus. Yeah? That look good? What's next? We want to get this product. Let's keep going here, mechanism.
It's going to associate with the aluminum, then shoot another hydride, right?
What do you want to do next?
Aluminum attached to the nitrogen attached to the
Okay. Okay. That's actually right. How do you know that?
Because it's somehow
Okay, good. Ultimately, we need 2 H's on the carbon. The H's here are going to come from workup. But what you don't really want to maybe do here is add another hydride and create an N2 minus. Okay? This probably becomes complex with the aluminum, because we got aluminum H3 here, yeah? The thing with these aluminum reagents is the aluminum can always act sort of as a Lewis acid at some point. And that can complex here. I'm just going to call this R. There's the H, double bond N. But now this is complex to aluminum, and we can draw these H's out. Now the aluminum is minus again, yeah? But the nitrogen is neutral. Now see, at this point, the aluminum is going to act as a hydride reagent again, because it's now mad, it's going to shoot out an H. And that can react again and start another process maybe. And we can show it as could just take away an H or something. I'm trying to finish it up here. If it acts as a hydride again, it becomes neutral again. Everything's neutral. And in comes another hydride. And so now we have two H's on the carbon, single bond to N. That's going to be a minus, yeah. And that's going to be aluminum H2. And basically, you put this in water, and you're going to get that there. Nitrogen will take a proton, and then basically the water can attack the aluminum and kick off the nitrogen, and nitrogen can pick up another proton. Not going to give full details here, a little bit convoluted here. We don't have time to go into the full details here. In the end, LAH will do the same thing as hydrogen, and hydrogen is analogous to reducing an alkyne triple bond. Okay? And ultimately, in the end, cyano group can be reduced down to the primary amine. And we're seeing that these hydride reagents can act as Lewis acids along the way in your mechanism. So this is more of an arrow pushing mechanism. The two H's from the carbon come from the hydride. The two H's from the nitrogen are going to come from workup. At one point, though, we had a double bonded nitrogen. Next reaction, diball H. What do you suspect that it may give with a nitro?
Double bond.
Double bond.
It only adds once. Okay? And this is going to give I'll draw the H. A lot of times it's not drawn here. And I bet you a lot of things that I could show this in another, I could show that same molecule drawn a little bit differently, and some of you would not recognize that it's the same thing as that. All right? I would love that not to be the case. Those are the fine details that if you're not past, you got to get past that. Yeah, that's it. This is N. Game over. That's it. Stops here. This we're going to work up in water. Just like LAH would require water workup, that does not require water workup. You add this into water, what are we going to do? This will protonate, and we will get that there?
What if, when you create the hydroxide from that, could that hydroxide attack the double bonded carbon and then kick electrons back onto the nitrogen, that nitrogen take another H so you can make an amine?
It is going to do something. This is not going to be the end product. By the way, this is called, first time we've said this, this is a carbon double bonded nitrogen. What type of functional group is this? It's an imine. Carbon double bond nitrogen. Imine. You're making an imine in lab. Not this way. This imine is not going to survive here. This is going to be hydrolyzed. That will be hydrolyzed. And that will take us to test 4 chemistry. We will not do that here.
So if we see like a reaction with this, do you want us just to go to the amine and stop right there? Or
Yeah. What happened here? A single addition to the nitrile to give the imine, it will not further reduce it. The imine just sits there until you add in water. When you add in water, the imine will actually get hydrolyzed.
Instead of adding water, can you add with magnesium just to have it sit with the nitrogen to keep it longer?
so you can use it as a nucleophile?
Well, that reminds me, brings up something. There's always something sitting with the minus. You cannot have a minus without a plus. That's actually an important point. There's got to be a minus, a plus there. Or if it's not a plus, it's coordinated with the aluminum and it's neutral. Okay. And by the way, this is going to give an aldehyde. Ultimate product would be an aldehyde.
So Dr. Stevens, what is our?
Because if under my hand is an oxygen, what do you have there?
An aldehyde?
Carbonyl or aldehyde?
Aldehyde, yes. Nitrogen is going to get replaced with an oxygen. Okay. We'll look at that mechanism during test 4. Okay. How we do on these below here? You can work on those. Let's look back at the previous handout. Questions about that handout? On the back of the blue handout we just got through is the synthesis of Allegra. The last step in the synthesis of Allegra is reducing the ketone to the alcohol, racemic alcohol, using sodium borohydride. Okay? Now often you can have other additives here, but sodium borohydride is the main reagent there. And there's actually a variety of other reactions here that we should know. For example, ester hydrolysis. You've got the acetate there. The acetate's hydrolyzed to release the alcohol. And the acetic acid is not even shown because it's just a waste product. Sort of a convoluted two-step oxidation. I don't know why they do it like that. You see the primary alcohol is being oxidized to the carboxylic acid. For us, we would just use one of the big three. I'm not sure why they did that. Maybe they've got these nitrogens over here. It's probably why they had to be careful, because if you used a big three, you're probably going to oxidize the nitrogen. And so they got multiple functionalities here. So usually these types of handouts here, I give you a number of these whenever I kind of handwrite something in there. That sort of stuff that we have done. Actually, there was a lab in Organic 1 where I showed you this Oh, I know what it was, when we hydrated an alkyne in organic 1 to make a ketone. It's not here. There's another way to make Allegra, I think. You have to look back at organic 1. Or maybe it wasn't Allegra, maybe it was Zyrtec, I can't remember, but I showed you this, I think, in organic 1 when we hydrated an alkyne. Okay, I hate to rush at the end here. Test on Monday yet? I'd be willing to move it to Wednesday if you like. I hate to rush and rush into a test. We could see what type of questions there are first thing Monday, but then Monday we need to move into test 4 material. Is that okay?
Yes.
Yes. I think test on Wednesday would be better. There's a few miscellaneous things we still need to look at. How do we do on this here? Anybody look at this warm-up? How can we go from A to tramadol? What do we need? Anybody got an answer here?
Attack it with like a Grignard reagent or a Grignard. And then
Yeah. Don't be a Grignard. Or analogous. I mean, Grignard is the most common for what you need. It's very straightforward synthesis there. You need certainly, as again, very straightforward, very basic. You need to know that type of reaction. How are we doing synthesis of fentanyl? Anybody got a synthesis yet? I doubt you do because there's multiple chemistry we need to cover. This is taking us home here. But as I mentioned, main functional group here is an amide. Do you know how to make amides?
yeah.
I think your last step would be to make your amide. That isn't going backwards. Your first step going backwards. Basically, you want to start breaking this molecule down into a smaller molecule. What bonds can we break or coming forward form? The last step here, I would say, is to make your amide. So, how would you make the amide?
Could the lone pair on the nitrogen attack the bottom of the aldehyde, those electrons go up, and then you can attack there's going to be a dipole created, and you can attack with it.
You're looking here?
No, sir, towards the top.
You're looking here?
Oh, yes, sir.
Where are you looking at?
I think we're synthesizing fentanyl.
Yeah.
Okay, I'm going backwards. Sorry.
But what are you looking at? You're looking at here?
Yes, sir. I was trying to reverse the reaction. My mistake.
What do you mean reverse the reaction?
I
What
was
reaction are you
going
looking
back to
reverse? Do what?
I was working backwards. And,
Working backwards from here there.
yes, sir.
Okay, that's what I'm saying. Let's work backwards from here. Where are you going to?
The lone pair on the nitrogen. And we go and
Well, that's again, lone
Other
pair on
nitrogen.
which nitrogen?
that nitrogen, sir.
Top one.
The top one.
Top one?
Yes, sir.
Okay.
And then kick electrons up to the oxygen at the top. And then
You want to kick electrons to the oxygen.
yes, sir. No.
And use some more.
Kick them off on the wrong foot.
Are you talking about drawing a
Resonance
resonance?
structure.
Maybe
Drawing
make
a
a
resonance
resonance structure,
structure?
is that what you're saying? Like, move the electrons in and push them
Yes.
up off? onto
Okay.
the-
I think that might, I don't understand why you would do resonance there.
You could make this a leaving group, perhaps.
Like what leaving?
I'd have to draw. I can't explain it very well.
Drawing is very good. Anybody got a synthesis here? Any questions for Ian today? Okay, guys, have a great day. See some of you in lab.